Good morning, everybody. I'm Eduardo. I did like the introduction yesterday, related with CITCEA-UPC Center. Good morning. So today is I would say the HVDC day. So in the morning you're going to have two different talks. The first talk is about HVDC technology. So it is an introduction of the converters that we are using on HVDC and basically the technology that we are using, or the industry is using nowadays. The second talk, the title is HVDC grid. So it is a bit more related with it's not focused on the technology. It's focused on the grid, and it's focused on the operation of the grid, how you control, for example, a multi-terminal HVDC grid when you have different DC nodes interconnected between them. So that's basically what you're going to see today in the morning, and then in the afternoon you're going to go to IREC. It's a kind of similar research center as the one that you visited yesterday. It's not here in the university. It's outside this building, so it's actually in the other. So you know this street is Diagonal, so it's in the other end of Diagonal, in the sea, close to the sea. Okay, so well, basically this is what we're going to talk about, and I don't know if this thing is working or not. Yeah. So well, I am Eduardo. I didn't introduce myself yesterday a lot, so I'm a PhD student here at the university. I'm also a project engineer in CITCEA-UPC, but I'm doing the PhD here on the UPC. Then you're going to, I think that you know Carlos Collados. I would say that he is the contact point for any doubt that you have regarding KIC here in Barcelona. Also, I mean, you have the university guys, and this is our guy. So he is, when we have a problem with KIC or whatever we want to do, he is the guy, and he will talk a bit about the history of HVDC. Then Joan Sau is this guy here. So he's a PhD student. Also, he's working also on CITCEA-UPC. And he is pursuing also the PhD. He has started like 1 year ago, something like that. Yeah. So he will talk a bit about DC-DC converters and how to control the power flow in the HVDC lines. Then Abel, he's a project engineer at CITCEA, which is another company. He is also pursuing the PhD here in the university, in the UPC. He's part of a European project. It is called MEDO project, and he's from Portugal, so he came here to study the PhD. He has been here for 2 years, so he will talk about VSC converters. The converters basically that are the workhorse converters that we are working, the more used converters in the HVDC technology nowadays. And then Atta, he's working on, he's not here right now, I think. I'm missing him, so hopefully he will be here when he when he needs to talk. But he will basically, he's working on EFASEC. It is a Portuguese company. He's also part of this MEDO project, this European project, and he's pursuing the PhD also on the University of Porto. And he will talk about HVDC protections, which is basically what they are doing in EFASEC. Okay, so what are we going to discuss about? It's HVDC, right? So you know HVDC, have you heard about it before? You know what's that, right? So HVDC is quite clear, right? High voltage DC. So you have, for many years, we have had this high voltage AC transmission, and well, we had some HVDC links, but now with different things that are going on, like offshore wind power, like the reduction on the price of the power electronics and other stuff that we were going to explain, we have more impact on the industry. HVDC has a strongest impact on the industry, and especially on transmission industry. So here I've included basically something which is quite illustrative for you. So Here you can see in these slides, we are using HVDC, for example, for interconnecting to different AC points, which could be an offshore wind farm and the main AC grid, to different long separated AC grids. You will see these applications today. So the idea is this: you have AC, you have a converter, and then you are transferring to DC. You transfer this power for long distances, and then you have AC. Right. So this is the main topic that we're going to discuss about today. So when this thing started, so well, introduction. Yeah, this is all the topics that we're going to do. So HVDC introduction, history. I more or less, explain all these topics: MsC converters, submodel description, DC-DC converters, power for control, and protections. Okay. And then we see a final case that is the case. I don't know if you know this connection between Spain and France that is done in performed in HVDC. So I'm going to show you a video about that, and you will see that it's quite interesting to see. Okay. So when this thing started, this is this is something that you can find. Even you can find a T-shirt with that if you like the image. So this thing started with what is called the war of currents between Tesla and Edison. So Edison was they were defending the AC was defended by Tesla, and the DC was supported by Edison. And this is something that I wanted to illustrate you to to start with something funny. But I would say, how do you choose between DC and AC? It depends a lot on the application. For example, for transmission, for many years we have decided to install AC, of course, transformers, rotating machines, etc., etc. For DC, for transmission, you have some specific applications where DC is more efficient. It's cheaper. So that's the preferred option, right? So it really depends on the application. Even for low voltage applications, for example, all the power supplies of laptops, batteries, and all that stuff. It depends on what you want to use, what you want to it's basically depending on the application that you select, one technology or another. It depends also on what you want to supply, which is your load, if it's in DC on DC. On DC on AC, or if the power is generated on DC or in AC, right? So there's always these hybrid configurations. But this thing started like a long time ago. So here's the numbers. So we had Edison and we had Tesla. Just a brief introduction of that. And even Tesla was supported by Westinghouse, which is the third actor here. Okay. And this is called the war of currents. And I would say that AC, for talking about transmission systems, AC won the battle because of three main points, right? Well, I say here, but not the war, because this is it never ends, right? So here, right now, the long distance transmission is fully dominated by the HVDC, right? And some people are talking about introducing other stuff in DC, even in medium voltage and DC distribution grids. So this is a battle that never ends. But at that point, for many years, everything has been done in AC. And why? So there were the three main key points. The first one was the transformers, right? So we could, to transmit voltage efficiently, what we want is to step up the voltage a lot in order to reduce the current for the same power amount of transmission, right? Because if you have higher voltages, you have less current flowing through the circuits, and then the Joule's law is what you mean, what you know. Okay, so transformer was the main decision changer. Then the AC machines, we are producing in all the power plants, energy using AC machinery. Basically, even wind power plants at that time, maybe conventional power plants like fuel, coal, whatever, use synchronous generators that are AC machines. So if you are generating power in AC and you can step up that power in AC, why to go to DC, right? And then also something that Atta will explain later, which is breaking DC current was difficult. How do you protect the grid? So you cannot really protect, it's difficult to cut a DC current, right? So what we do today is we wait until the this alternating current crosses 0 to open the circuit if there is a fault, if there is a short circuit or whatever it is there. But if you want to break, a constant DC current flow, it's difficult to do that because the technology that we had at that time and even today is something challenging, and Atta will give us a speech related with that. So, but at that point, AC was the main technology used for transmission, but there were some specific applications. For example, in 1984, Carlos will explain that later, and Abel also. ABB proposed something. It was a CE, I think, at that time. So, Professor Umolam were working with some these mercury arc bulbs to use them as transistors, kind of. So they did like the Gotland link, and this was in 1954. You see that the power was reduced. There were quite few amps, some 100 kilovolts. So that was the first transmission in DC, important transmission in DC. Okay. So as soon as they started working on that, for example, GE in 1972, they did this Eel River converter station, which was based on thyristors. So as soon as the technology was evolving, we started to see more HVDC links, especially for long distance transmission. But the main transmission was done in AC. Okay. Then this is basically the technology that we have today is voltage source converters. You will see that later. And this was the first in 1997, the first important link that they were testing this technology. And as soon as we were improving the technology, this HVDC has become a bit more I would say mainstream. So we will today we see more links than 50 years ago. 50 years ago everything was done in AC. Right now you have some applications related with that. Okay, so which are these applications? Basically, we have three different applications, important ones. The long distance power transmission, for example, this is between Xi'an, Java, I don't know if I'm pronouncing it properly, and Shanghai. So, the total length is 2,000 kilometers, so it's a very long line. And, due to the reactive power, if we have done that in AC, just the reactive power losses, it won't be technically possible. I mean, unless we are compensating this reactive power with capacitor reactors or whatever. So that's something that has been done by ABB in DC. So the power rating is 6.4 gigawatts, so it's quite a lot of power going through this line, and the DC voltage is plus minus 800 kV. So it's a huge. We are talking about huge voltages, large power, large installations. You will see some pictures about it. You will see that they are like 2 or 3 or more football fields wide and long. So they are quite huge things. Why are we using also HVDC? We are using HVDC to interconnect non-synchronous networks. So imagine that if you have two different networks that are not, are operating asynchronously. In Europe, we have different UK and France, Russia. I think that Abel will explain that a bit later. So how we interconnect that? We can have asynchronous networks working at 50 hertz, even at the same frequency, but asynchronous. We can interconnect them, and which is this case, for example. And then we could have also different frequencies, 50 and 60 hertz frequencies. This is the case of, for example, this Brazil-Argentinian interconnection. Okay, but here you can see that the ratings are, typically a lot of power. In this case, not a lot of voltage. It's not a really high voltage, but the power is quite high always. So you will see that these HVDC transmission systems are always transferring a lot of power. Okay. And then another important application, which is basically important today, is the the undersea cabling. Okay, if as soon as you have to save some underwater cables or underwater distances, you will choose HVDC, because it's difficult, for example, to compensate reactive power in an undersea cable, because it is grounded under the sea, right? So it's not easy as, for example, an overhead line. So if you have an undersea connection, you will definitely go for an HVDC link, right? So that's basically why offshore wind is strictly related with HVDC. As soon as you have a wind farm which is located far away from the shore, you are, definitely you have to go for HVDC. That's why everybody's talking about HVDC lately, because they are installing manufacturers, and the European Commission is pushing for a North Sea European grid offshore for integration of renewables, especially offshore wind power plants, and this grid has to be done in HVDC. Okay. So 3 different ideas why HVDC is better than AC in some cases. First of all, the investment cost. I must say that, for example, the initial investment cost, for example, if you compare just the cost of the installation, of course, transformers are cheaper than converters. So transformer is copper, iron, and whatever it is, but they are huge, of course, and they are complex to design. But there's nothing to do. There are not power electronics. There's no really intelligent controllers that must control the whole converter to transfer power. So they are just this is something that is cheaper, and here you can see the difference that is huge. But in this axis you have the distance. Okay, as soon as the distance goes by, so for longer distances, you will see that that HVDC is cheaper than AC. And that's why, for example, when we have an offshore wind power plant, we are going for HVDC instead of HVAC, right? Because it is basically cheaper, and everything is about the money. Okay, so that's something. And even it's something which is interesting, that for example, for overhead lines, this critical distance moves. So for overhead lines, the distance is between 600 kilometers and 700 kilometers, 1800 kilometers. Okay, where this break-even distance, where you prefer AC or you prefer DC. But for example, for subsea cables, and that's why offshore wind farms that are located like 100, 200 kilometers far away from the shore are being installed or integrated with HVDCs because of that. Because around 50, 70 kilometers you prefer to install, it is cheaper to install HVDC than HVAC, right? Okay, another thing is something that you can imagine is the losses, the transmission losses. Okay, you see that, for example, in the AC you don't have any reactive current, in DC you don't have any reactive current through the circuit. So you don't have, in DC you just have the active power flowing through the circuit, no reactive power. So it is something that, it is interesting to see that losses. This is the AC losses are even almost higher for shorter distance, even more or less at 400 or 250, something like that. Okay, the losses in converter stations, for example, is around 0.611%. So they are getting better, but it is something that you can imagine that, for example, from 1% to 0.5% of losses of a lot of 1 gigawatt, there's a lot of energy lost there, right? So it is something that is really, really important. If you want to improve your line, you want to improve your converter to win, for example, I don't know, if you are a manufacturer, you want to commission something, I think that it's worth to press this efficiency, because then you can offer something much better than your competitor. So that's why these efficiencies are quite low right now, and VSC is evolving, so it's getting closer to the LCC technology. Okay, and then another important thing is the visual impact. So here you can see, for example, a transmission line in AC. This is the AC overhead line. These are more or less ideas for the same power transfer capability. Here you can see the AC transmission line. Here you can see the DC overhead line. But you know that we could do, DC underground cables. For example, this is the INELFE project. This is in the last part of the presentation. I will show you how has this thing been done. This is crossing between Spain and France, and the cable is this is a DC LAN cable. So it's something that worth it in order to avoid large towers going through the Pyrenees, and it was one of the important key points here. Okay. Well, an example how these things look like. So, for example, this is an interconnection between an island and the main AC side. So imagine that this is the mainland and this is the island grid. So here you have AC transmission systems, because, for example, our power generators in the island, everything is done in AC, and we have also in the mainland, our main AC grid. Everything is done in AC, of course. But if this distance is long enough, and should be larger than 70-80 kilometers, we will go for HVDC. So what we need is 2 different converter stations to transfer from AC to DC, and then AC back to DC. So DC to AC again. The thing is that this is typically bidirectional, but most of them are only working in one direction, because, for example, you can imagine that as an island, what you typically do is you generate your power, but mainly if you have an HVDC link, what you are doing is to absorbing an energy from the mainland where the powerful generators are installed. Okay. Another important application of that is the offshore wind. So here you can see that there's the 2 combinations of 2 different reasons. So you have long distance and an undersea cable. And here you can see that you will have these offshore wind power plants located really far away from the shore, and then you're collecting everything mainly in AC. There are some proposals for doing the DC collection wind farm, but mainly this is you have a rotating synchronous generators producing power in AC. So you are collecting everything in AC, and then you are gathering all the energy here in the substation transmission system, and then you have a power converter there to transfer from AC to DC. You transmit all that power through this line to the main AC grid, and then here you have another power converter to inject this energy to the grid, right? So this is another interesting application, and probably this is the star application for HVDC today. This is one of the most used technologies that, for lately we have these long distance power transmission systems, but this is something that HVDC will be used in the future. And